Look, every single producing well out there is fighting a losing battle against declining reservoir pressure. It's just a fundamental fact of physics, right? You can't negotiate with the rock, and you certainly can't wish the pressure back. From day one of production, that pressure is steadily dropping, and if we don't intervene, the flow rate of those hydrocarbons declines right alongside it. So, a field's economic life ends way earlier than the actual recoverable reserves would normally allow.
Okay, let's dive into this, because the immediate question looking at this grim reality is, do we just accept the inevitable flow rate decline? Absolutely not. While we can't stop the reservoir from depleting, we definitely don't have to accept that steep production drop-off. We can intervene. By using subsea boosting, we literally add energy back into the system right at the seabed. This can extend a field's economic life by years, sometimes a decade or more, past when it would otherwise become uneconomic.
Section 1. The problem and the solution.
So, subsea processing and pressure boosting is basically a life support system for an aging well. The primary mechanism here is adding mechanical energy back into the produced fluid right down at the seabed. Its entire job is to lower the pressure the well has to work against. If you look at natural flow, as reservoir pressure drops, the operating point just helplessly slides down that natural decline curve. The flow rate just shrinks. But with boosted flow, by adding a subsea booster pump, we overcome the system resistance. We pull significantly more fluid out of the reservoir than natural flow alone could ever achieve, literally jumping our operating point to a much higher flow rate.
Section 2. The mechanism. Inflow performance relationship.
To really get how this works, we need to understand the inflow performance relationship, or IPR. This is the fundamental relationship between the wellbore flowing pressure, so the pressure right at the bottom of the well, and the achievable flow rate. It dictates exactly how much you can get out of the ground based on downhole pressure dynamics. Grounding ourselves in this IPR concept is absolutely crucial to understanding why boosting actually works in the real world.
Let me break this down into plain terms. Imagine you're drinking a super thick milkshake through a straw. When the glass is full, high reservoir pressure, it flows easily. But as that milkshake runs low, it gets incredibly hard to pull the flow up through the straw, right? Your lungs have to work way harder. Well, a subsea booster pump is essentially like switching to a massive, highly mechanized, incredibly powerful straw that can keep pulling a heavy flow, even as the glass is almost completely empty.
Section 3. Decoding Fetkovich's equation.
Now, as engineers, we obviously don't size billion-dollar subsea hardware based on milkshakes, so let's look at Fetkovich's equation. It proves the concept and dictates the design. Think of the variables here like characters in a story. Q is our hero, the flow rate. Q is a function of two main pressures, PR, the declining reservoir pressure, and PWF, the wellbore flowing pressure. The absolute open flow potential, or AOFP, just sets the maximum theoretical limit.
And this brilliantly illustrates exactly where our booster pump intervenes to literally hack the equation. Check out the math. We have 1 minus the ratio of PWF to PR. Since we have zero control over the declining reservoir pressure, PR, our only move is to manipulate PWF. By adding mechanical energy, we actively lower that wellbore flowing pressure. Shrinking the numerator increases the whole bracketed value, shifting our operating point on the IPR curve and directly increasing our flow rate, Q. It's just a beautiful mathematical proof.
Section 4. Subsea boosting hardware. So, how do we actually execute this thousands of feet underwater? Let's compare the heavyweights, multiphase pumps and electric submersible pumps, or ESPs. Multiphase pumps are these rugged units that handle a direct, unseparated mix of oil, gas, and water. ESPs, on the other hand, are fascinating. Instead of being stuck down in the wellbore, seabed ESPs can be installed vertically in dummy wells, horizontally on permanent bases, or even directly integrated as jumpers in the existing subsea architecture. The advantages of these seabed ESPs make them incredibly attractive for deep water operations. For starters, you can often deploy them using lighter construction vessels of opportunity, instead of renting a massive, hyper-expensive drilling rig. They also offer great redundancy since you can easily configure them in parallel. Plus, they utilize existing subsea flowline infrastructure, making them a super cost-effective way to get high volumes moving while minimizing deferred production.
Section 5. The strategy. Economics of timing. Now, what's really interesting about this slide is that installing this massive equipment is a highly strategic timing decision, not just a technical default.
A great rule of thumb from our sources is this: Think of subsea boosting like adding a supercharger to an aging car engine. Subsea boosting does not create new reserves. It doesn't put oil in the ground that wasn't already there. The reservoir engine is naturally losing power over time. The subsea supercharger simply forces more performance out of what remains, letting you access those existing reserves faster and way more efficiently. You can see exactly how this supercharger effect plays out over a well's life cycle. First, oil starts with high natural pressure. Then, natural decline predictably sets in. Eventually, you start nearing the economic cutoff, where operating costs eclipse revenue. But right before that cutoff, bam, we trigger our boosting intervention. That single action shifts the whole curve, buying meaningful, highly profitable extra years, sometimes a whole decade of extended service life.
I really want to emphasize the economic tension here. Timing the investment against the actual decline curve is what makes the billion-dollar economics work. If you install it too early, you're wasting capex on a well that didn't need help yet, like putting a supercharger on a car that's already winning the race. But if you install it too late, the field has already crossed below economic flow rates, and you've permanently stranded reserves that boosting could have easily kept flowing.
So let's summarize what most people miss with these systems. Yes, boosting accelerates existing recovery, but it significantly adds to both your CapEx and OpEx. Plus, subsea reliability is a massive risk. If an unplanned failure happens on the ocean floor, you don't just lose the pump's added pressure, the well drops straight back down to its natural, unboosted IPR curve. This can cause an abrupt, sometimes catastrophic loss of flow that will completely shock your topside processing facilities.
The physics of reservoir depletion are entirely out of our hands, but the financial strategy is squarely in them. Subsea boosting is this profound intersection of fluid mechanics and economics. So, if natural decline is an inevitable fact of your field's life cycle, are you timing your subsea intervention to truly maximize your economic recovery, or are you just leaving viable reserves stranded in the dark? Think about that for your next field development architecture. Thanks for joining me for this explainer, and keep questioning the physics behind the flow.